Assalamu alaikum and a very good day. My name is Muhammad Izzan bin Abdul Samad, metric number P112520002. Now I am presenting my research proposal defense, which is titled Neural Network-Based Stability Guarantee Control for Nonlinear Electrohydraulic Systems. This presentation will be consisted of 8 main sections as shown here, which will be covered in each of the slides, which will be shown later on throughout this presentation. I chose electrohydraulic systems due to it being the backbone of heavy industries due to the high force-to-weight ratio and the demand in response to the Industry 4.0 transition and addressing the issues of energy and cost savings. It also is within the alignment of the United Nations Sustainable Development Goals, SDG 9, as well as the high market demand based by region in the year 2025 shown in this chart, and based on the Asian Pacific market as shown in this chart here. Here are some of the many common engineering applications of electrohydraulic systems, in which the most common ones are the press machines and the excavator machines. Among the problem statements found in terms of the technical gaps are the coupled physical nonlinearities of the electrohydraulic systems. Some prime examples are the frictions, the fluid compressibility, as well as the valve dead zones. And in terms of conventional controller limitations, fixed PID loops cannot adapt to parameter variations. Sliding mode controllers introduces chattering, which affects the actuator's performance, and model predictive controllers require accurate models for real-time implementation. The problem statements in terms of safety gaps are in terms of the lack of formal stability guarantees, which is the limited stability analysis through Lyapunov-based stability proofs, the risk of uncertainties due to the parameter variations, and the idealized assumptions which may not be held in practical applications, and in terms of simulation to real deployment gap, which is specified to real-time implementations of the controllers, the hardware integrations of the controllers, and the existing yet limited experimental validations available. In terms of the research scope and boundaries, it is focused towards the physical test rig platform, the uncertainty parameters, which includes load profiles, internal leakages, and external disturbances, the intelligent architecture of the controller, the development ecosystem, MATLAB or Simulink, and the hardware interfaces that are present during this research. And the exclusions of this research include no reinforced learning, no multi-access networks, and no embedded field programmable gate array, or FPGA. Among the questions asked throughout this research is that how can this controller be designed and trained to capture the nonlinearities under various load profiles? How can this architecture be integrated into the controller, and its tracking stability can be mathematically proven using the stability theory? And how does this controller minimize tracking delay and suppress the chattering on the physical system itself? The hypothesis of this research is that this controller will compensate for unmodeled time-varying nonlinearities, achieve the guaranteed theoretical stability, overcome performance degradation, and with improved tracking accuracy, enhance robustness against variations, and disturbance rejection during real-time implementation. Among the objectives of this research is to develop a data-driven neural network dynamic model to design the stability guarantee control framework, and at the same time to experimentally validate and benchmark the controller against the standard PID and classical SMC. Among the physical gaps that have been identified throughout the literature review is the stick-slip friction found by this study, the internal fluid leakage found by this study, the bulk modulus variations or shifts in oil stiffness by this study, and most importantly, the valve dead zones found by this study. When benchmarking the controller architectures within this literature review, it is found that some have limitations, such as the lack of adaptability in conventional PIDs, the introduction of harmful chattering in classical SMCs, the constraint mismatches in model predictive controllers, and in terms of adaptive robust controllers, the need for handcrafted analytical models. And in terms of other studies, such as this one, there is no neural network learning here. This one introduces controlled chattering, and this one hasn't been validated on complex electrohydraulic systems. Based on this developed K-chart from the literature review, there are several research gaps that are identified, but the main one is there is no unified framework which integrates MLP-based learning, Lyapunov stability guarantee, adaptive robust control, and real-time physical validation. This is the overall methodology flowchart that will be used and carried out throughout this research and will be later explained in terms of 6 phases. To fulfill Objective 1, a comprehensive literature review on existing studies is carried out. From there, we specify the limitations of control strategies to establish constraints and research gaps. And then we develop the mathematical system modeling, which is then validated. If the validation fails, it is refined and corrected before moving to the data-driven modeling. To fulfill Objective 2, first we collect the data as shown here, and then from this data we develop, train, and optimize the neural network modeling for the next phase, which is designing the controller based on the neural network model, and then we carry out the stability analysis. If the stability criteria is not met, we either redesign the neural network model or redesign the controller itself before moving to the final 2 phases. Finally, to fulfill Objective 3, first we carry out the simulation validation under nominal conditions, then we carry out the experimental validation in the laboratory scale physical hydraulic system, whereby the executed final performance evaluation to assess the tracking accuracy, robustness against parameter uncertainties, and external disturbance rejection. The expected outcomes of this research is that a validated model is created with high prediction accuracy, a controller with Lyapunov-proof stability, and a validated controller with improved tracking and robustness. Here is the expected timeline graph of the research, which covers within the span of 3 years or 12 quarters to fulfill all 3 objectives. Among the contributions of this research is that this research aims to develop a hybrid control architecture, a theoretical safety certificate, which is mathematically proven using the stability theory, a dynamic uncertainty estimation using online learning, and a framework that bridges the gap between the simulation to hardware gap. And in terms of the industrial and societal impacts is that this study becomes heavy industry reliability, energy and wear reduction, supports the SDG 9 by United Nations, and guaranteed operational safety during fail-safe operations. In conclusion, this study aims to directly address the absence and formal stability guarantees typically found in standard intelligent control architectures and ultimately aims to deliver an efficient control strategy that enhances operational reliability and energy efficiency in industrial automation systems, which supports the United Nations SDG 9. Here is the list of key references which is used as a guide throughout my research. And these are the additional and related references which are also used throughout this research, as well as the links of the image sources used throughout this presentation. That is all from me. Thank you for listening.